Hey everyone, so today I'm going to be teaching binary search. And binary search is one of the most common coding patterns you'll see in coding interviews. So make sure you really understand binary search. And yep, in this video I'm pretty much going to be teaching it. So first off, what is search? Searching is, in the context of what we're doing here, is finding some target in a data structure. So let's go into linear search first, which is more a basic form of searching. And then we'll go to binary search, which is more efficient. So in linear search, we're searching for some target, and we need to scan the data structure from left to right looking for the target. So as soon as we see the target, we return it. And this requires some sort of linear data structure, such as an array or a linked list, where we can traverse it from left to right. So let's look here. Pretend we're looking for the element 7 in our array. So in a linear search, it's called linear search because we just start a pointer at the very left, and then we pretty much move it from left to right, scanning linearly. It's a tongue twister, from left to right. So how does it work? Pretend we're looking for target 7. We start the pointer all the way in the left, and we start looking for this element of 7. Is -10 7? No. Is -5 7? No. Is -3 7? No. Is 0 7? No. 1? No. 3? No. 4? 5? 7. Finally, we see the 7, and we could, let's say, return true that we found it. So that's how linear search works. It just scans from left to right. Pretend we are looking for an element that's not in there. Again, we start at -10. No, -5, -3, 0, 1, 3, 4, 5, 7, 10, 14, 20, and none of those are 8. So when we get to the end, we return false, that we couldn't find the target. So you could see in a linear search, we're pretty much cutting the search space by one element on each iteration. And this leads to an O-Ven solution. O-Ven solution is worst case, because worst case, if the element is not in there, we would have to have traversed the whole array just to find out. And pretend worst case we're looking for a target of 20, then we would have had to traverse the whole array to finally find the target of 20. So that's why the worst case runtime is O-Ven. And we're only cutting the search space by one element each time. You can see here is negative, because first we'll look at -10. Is -10 the target? Nope. So we go here. And then is -5 the target? Nope. So we go here. Is -3. You can see that we're just cutting the search space by one element. We're saying that element can't be it, and let's look to the right, and we're just crossing off one element at a time. That's linear search, and it leads to an O-Ven solution. But we could actually do a lot better with the binary search. But the only thing is that a binary search requires the search space to be in sorted manner. And I'll show more specifically what that means. But binary search is a more efficient way to search, because instead of scanning elements from one by one from left to right, as we do in linear search, binary search starts at the middle, and then we can cut the search space in half by repeatedly comparing the middle element. And I'll just visualize that to make it a lot more clear for you. So like I mentioned, the array needs to be sorted, but instead of starting our pointer from the very left here, pretend we're looking for 7. Pretend we're looking for 7. So with linear search, right? How long did that actually take us to find 7? Well, it took us 1, 2, 3, 4, 5, 6, 7, 8, 9 iterations to find 7 in our search space. Now let's instead of just starting the pointer from the left and the right, or all the way from the left and scanning from left to right, let's start the pointer in the middle somewhere. Let's say the pointer is at 3 here. Let's say this is the middle. So this is what binary search does. It looks at the middle element, and it requires the array to be sorted. Because if the array is sorted, I know when I'm looking at 3, I know that since the array is sorted, all the elements to my left here are less than 3, and all of the elements to my right are greater than 3. So pretty much I compare 7 with 3. I see that 3 is less than 7, so I know that the element that I'm searching for is not 3 for sure, because it's 3 is less than 7. But I know that all the elements to my left won't be 7, because all the elements to my left are less than 3 also. So by the process of elimination, I could already eliminate half the search space. So I never would have to search those elements because I know they're less than 3, and 3 is less than 7. So now we're left with this search space right here. Let's look into the middle of this search space. Let's look at 10. So with 10 here, pretty much 10, we compare 10 to the value we're searching for. 10 is greater than 7, so I know 10 can't be the target, and all the elements are greater to the right are greater than 10, so my 7, that element I'm looking for, can't be there either. So this is one iteration, this is 2 iteration. We again cut the search space that we're left with in half again. Now let's go to 5. 5 is less than 7, right? So since 5 is less than 7, 5 can't be it, and anything to the left of 5. So that's the third iteration here. And then finally, we get to 7, and that's our target. So with a binary search, it took us just 4 iterations. In the 4th iteration, we found we found what we were looking for way faster, right? Pretend this array was way larger and that had way more elements. We'd be able to cut the search space by a lot more elements on each iteration each time. So it's super powerful. That's essentially what binary search is, and it requires a sorted search space in order to cut the elements in half. Because imagine the array was unsorted and we are looking for -20, right? Pretend we try to binary search, we look at 5. Since it's not sorted, we don't know if -20 will be on this side or -20 will be on this side. Because since it's not sorted, we can have elements that are less than 5 here and elements that are less than 5 here also. So we need to kind of search both. So if it's unsorted, linear search is pretty much the only thing we can do here. Let's see. Yeah, so cool. So when we do a binary search, we can search for an element in a data structure like what I showed there, but we could also binary search for a specific value. And I'll show examples of both of these different ones in my when I walk through some questions in a second. But for searching a value, we could think of it something like this. Pretend we're trying to figure out how many punches I need to throw in a fight to hit 300 punches by the end of the fight, right? And pretend we have 12 rounds. So pretend, let's say I'm gonna throw seven punches around. I extrapolate that out by 12 rounds, 7 times 12. If I see that, what is 7 times 12? 7 times 12. It only equals 84. So I know if I throw anything less than 7 punches, I won't ever hit my target of 300 punches in a fight. So I won't. Definitely I won't throw 6. Definitely I won't throw 4. Definitely I won't throw 3. Right? So maybe I'll try something else. Maybe I'll try throwing 50, or I'll try throwing 50 punches in a fight. What's 50 times 12? Equals 600. Sorry, equals 600. 50 times 12 equals 600. I want to throw exactly 300 punches in a fight. So 550 punches each round is too much. So I need to do less, and I shouldn't try 51, 52, 53, right? So that's a way you can binary search for value. But yeah, it's a bit silly in this example because you can just do 300 divided by 12. But I'll show an example or a question where you have to binary search for a value. So you're binary searching for like an optimal value in sort of the same way that I just mentioned there. But yeah, most of the time when you're doing an interview though, you won't have to do binary search straight up. You'll have to do some sort of modified binary search as well. And I'll actually show an example of a modified binary search question. But yeah, I mean, let's just get straight into the examples. So in this first example here, let's just walk through a simple binary search. So in this question, we're given an array of integers, nums, which is sorted in ascending order. And we need to look for a target inside of that number array. We need to write a function that search for the target in nums. If the target exists, return its index, otherwise return -1. We must write an algorithm with O of log n runtime complexity. The moment I start seeing log n, I start to think binary search. And it looks like all we need to do is just find a target, and it's in a sorted array, so it looks like just a classic binary search question. So let's walk through some of the examples. So pretend we have a number array here, and we're looking for target 9. Let's go like this. We have nums. So it says the output is 4. So why is that the case? Well, 9 here is actually at index 4. If we add the indices here, 0, or let me space this out. 1, 2, 3, 4, 5. Move the dot to make it look cleaner. So 9 exists in nums, and it returns, and it's at index 4. If we are looking for a target 10, or for example, actually in this case they're looking for target 2 in the second example, it's not in here, so we need to return -1. So yeah, this is the output. 9 exists in that. So how do we actually implement a binary search here? Well, how we do this is we usually start with 2 pointers, left and right, and left and right pointers here pretty much define what the search space is. So the left pointer is the left bound of the search space, and the right pointer is the right bound of the search space, and everything in between is still in the search space that we're looking for. So in this case, we start at, since left is here, we're all the way at index 0, and right is at index 5. The search space is all elements between indices 0 and 5. If the left was here, that means the search space that we're looking for is between here. So we initialize the left and right pointer. 0 length of nums -1. It's in an inclusive boundary. So if the left is here, we're saying -1 is part of the search space still. So it's inclusive to where the pointers are. So we'll say while the left is less than equal to the right, the moment that the pointers cross, that means we've exhausted the search space. So for example, the left goes here. If they're at the same element, that means the search space is that one element. But once the right and left cross like this, then it's not valid anymore, and we've exhausted the search space. So yeah, we start the pointers, one at the start of the array, one at the very end, and that means we're searching the whole array. And we'll say while the left is less than equal to right. We'll have our algorithm here, and at the end we'll return -1 if we couldn't find. That means we exhausted the search space and we couldn't find the element we were looking for. So now how do we, like I mentioned before, we need to find a middle element and then cut the search space in half based on the value of that middle element. So what's the middle element? Well, the middle element in this case, it's an odd length array. So there's actually two middles. You can see these ones are both in the middle. So we'll just take the middle at the bottom. We'll try to take this, right? So what we're gonna do in this code is get mid value and then cut search space. Or we have another case, like if the mid value is target, return that. Because if we actually found the target, we want to just return that and just notify the algorithm to stop. Let me adjust. So yeah, how do we get the mid value? Well, there's two ways. We can, to calculate mid, we can do left plus right. And do an integer division by 2. It needs to be integer division, so we get an integer that we can access the array. So for example, 0 plus 5 divided by 2 is equals to 2.5. So we'll say 0 plus 5 divided by, or we do an integer division. So 0 plus 5 equals 5 divided by 2 is 2.5, but since we're taking integer division, it floors it. So we actually, that's one way to get the element here, the middle. Pretend we are at 3 and 8 here. So what's 3 plus 8? 3 or 3 and 5 here. What's 3 plus 5 equals 8. Divide by 2 equals 4. You see how that accesses the middle element here? But one thing to know is don't do it this way, because this could lead to integer overflow. In Python, it doesn't really matter, but it's just bad habit to do left plus right, because pretend you have a really large left plus or left value, like the left pointer is really large. You can get into an integer overflow in some languages. So the more optimal way to do this is, it doesn't really matter in Python, but I want to show this way for other people who are using languages like Java where there could be an integer overflow, is you do left. What we do is we go left plus right minus left. I think then we divide that by 2. Let's see the math there. So what's left? Left plus right minus left. So left is 3. What's the difference between right minus left is 2. So what do we get here? We get left equals 3 plus, what's right minus left here? 5 minus 3 equals 2. So my math might be off there. Left plus, oh no, we do it like this. Left plus right minus left divided by 2. Something like this. And this is how we calculate it. We take right minus left divided by 2. What's right minus left? Right minus left is 5 minus 3 equals 2 divided by 2 equals 1. So we do 3 plus 1 and then we get 4. Right. So I guess the middle. So I'll do left plus right minus left divided by 2, and that could avoid integer overflow. You'll see in LeetCode that they do two different ways. This way. Do this way. Left plus right minus left divided by 2. So you're adding the difference between the right index and the left index to the left, but you're going to divide that by 2 because you only want to capture half the distance between those two values. So mid equals left plus, go right, minus left divided by 2. That gets us the mid. And then what do we say? If the nums at the mid is actually equal to the target already, then we just return the middle. We want to return that index. elif nums mid. If the middle element is less than the target, I can move my left pointer equals to mid plus 1. Because pretend we're looking for 7, right? I calculate the mid is here. 3 is less than 7. So I don't need to look at 3. And I don't need to look at 0 or -1. So since left is defines our search space, we're moving left all the way up to the index here, mid plus 1. Because we don't want to search the middle element again or any of the ones to the left of the middle element. That's why we're doing left equals mid plus 1. Otherwise, pretend we are looking for 0, for example, and mid was here. If 3 is greater, then since 3 is greater than 0, we can just do else right equals mid minus 1. That means we don't want to look at mid. We want to move the right pointer all the way to this side and not look anywhere on this side at all. So that's pretty much how the logic works. We're adjusting the left and right bounds of the search space. And let's run that code. Hopefully it works. Nice, it's 100% of the time. That's a simple binary search. Let's move on to a different question. So this second question is called Coco eating bananas. So in this one, it's a binary search question as well. But in this one, we're actually binary searching for a value here. And like a value here, and not just an element in an array. So the value that we're binary searching for is the rate at which we should eat the bananas. So I'll say we're binary searching for the rate that we should eat the bananas. So in this question, I'll quickly go over the prompt. There are n piles of bananas. The ith pile has that many bananas in it, and the guards are gone and will come back in 8 hours. So what that means, it's a bit weird, but we're given piles. So here we're given 4 piles of bananas. The first pile has 3, this pile has 6, this pile has 7, and this pile has 11 bananas. And then we're given an h. So h equals here. So we have 8 hours until the guards come back. So we need to figure out the rate at which we should eat the bananas. Our goal is we want to eat slowly, but we still want to finish all the bananas before the guard returns. So constraints here. So Coco likes to eat slowly, but still wants to finish eating all the bananas before the guards actually come back. So the first example, the answer is 4, and I'll walk you through that. But yeah, there's some other things to mention in the question. Pretty much, we need to decide on the rate that we should eat the bananas. So once we decide on a rate, we can't change that. For example, if we say we want to eat bananas at a speed of 5, what we're gonna do is we're gonna take a pile and eat 5 from it. If the pile has less than k bananas, we still need to eat 5, or we'll eat the bananas that are left over. But like for that specific hour, we can't eat any more bananas. We can't go to a different pile. So pretty much for every hour, we need to just choose one pile and then eat the k bananas that we chose. So what does that look like? Let's look at the answer here. Piles here, h here. So we'll say we're gonna eat bananas at a rate of 4. So our goal is to eat all the bananas before the guards return, but we want to eat them slowly. That means we don't want to finish fast, or we don't want to finish late. We want to finish exactly right on time. That means by hour 1, all these piles should be exhausted. So let's start at by hour 8, because they come back in 8 hours. All the piles should be exhausted. So what does this look like? So we're given 2, 3, 4, 5, 6, 7, and 8. By the time we get to 8, we want to have exhausted all the piles. So as the rules of the question say is, we need to pick a speed of k, and we'll say, okay, let's see what happens if we eat at a rate of k. So here we pick a pile and we eat 4 bananas. Since there's only 3, this goes to 0. And yes, we have capacity to eat more within that hour, but what it says here is we will not eat any more bananas if the pile has less than k. So for example, this only had 3, so we only ate 3, but although we have 1, we can't take from this one, right? That's the constraint of the question. So what happens here? For the first hour, we finish that 1 pile. For the next hour, this goes to 4. Sorry, this goes to 2. The next hour, this goes to 0, right? The next hour, we take another pile. We take the 7, and then we take from the 7 and we subtract 4. What is that? 3. We go here. That's 0. And then finally, for the last 3 hours, we just keep taking from this last pile that has anything left. So that's 7, 3. And you can see by hour 8, we exhausted them completely. So we know that k is a good rate that we should eat them. But the question is it the lowest? Well, if we eat 5, right? 5, since we're looking for the minimum integer k, even if 5 actually finishes in exactly 8 hours, it's still less than 4, so we don't care about that result. What about 6? It's still less than 4. It's still less than 7, right? But pretend that we chose a rate like 10, right? If we chose a rate or let's say we chose a rate of 11. And we'll backtrack here a bit. We'll remove this. Like, you'll see why binary search works for this question. It's similar to what I mentioned. Is pretend we chose a rate of 11. If we, by the first hour, we'll exhaust this one. Second hour, we take another pile and we eat 11. There's only 6 there, so it goes there. We exhaust this pile. And then by hour 4, we've exhausted all the piles. We literally ate them way too fast. So we know that 11 is too fast, but then we also know 12 is too fast. We also know 13 is too fast. We also know 14 is too fast, 15. You can see 11 and everything greater than it is going to be too fast. So we could just remove those from the search space and never have to look at them. Pretend we chose a rate like 3, and that was too slow. It took us more than 8 hours. We'll know that 2 is too slow and 1 is too slow. So you can see why we can binary search for values, because we can just pick a random rate and then we could see, was it too fast? If that was too fast, then we don't need to look at any rates higher than that, because any rates, if we eat any faster than that, we're going to exhaust the piles even faster or just the same. If we take anything lower, so like we need to take something lower because we need to sort of slow down how fast we're eating to hit exactly the 8 hours. Pretend we look at the middle and it's too low. If it's too low, then we know that if we even slow down our rate any further, it's going to become even slower. So we can eliminate all the things to the left of it. So that's exactly why binary search works here. And let me go ahead and implement it. So like I mentioned, the left and right pointer needs to be the left and right boundaries of your search space. So if we're given left equals 0, right equals, so what's the fastest rate that we can go? Well, actually the minimum should actually be 1, because we want to eat bananas, so 1 is the slowest rate at which we can pretty much eat them. What is the fastest rate we can eat bananas? Well, it's going to be the maximum, it's going to be the biggest pile. So the fastest rate we can eat bananas is probably 11, because that's the biggest pile. So if we eat at a rate of 11 and we have 4 piles, we can exhaust all the piles in just pretty much one go there. or like in exactly 4 hours. If we did 12, it's not going to make any difference because the largest element is already 11. So we could say our search spaces, we can eat at a rate of 1, or we could eat at a rate of like the max of the piles. And we're going to be searching for some result. So what we're going to do is here, while left is less than right, we're going to be searching for the optimal K. So how do we calculate the mid? This is boilerplate as well. Left plus right minus left divided by 2. I've already showed this in previous. So what we're going to do is mid is the rate that we chose. So now we just need to simulate what I did here of eating the different piles and seeing how many hours it took to eat the piles given a specific rate. Be like hours given hours to eat given the rate. So we're given self and we're given the piles and we're given the rate. So how do we calculate hours? So we'll say hours taken starts at 0 and we're going to return that. But what we're going to do is we're going to loop through the different piles. So for pile in piles, what we're going to do is how long will it take us to finish that pile given that rate? Well, it's going to take us, if we're going to do hours taken, we're going to create a sum of all of them, but we'll say pile divided by the rate. So that's how long it will take us to finish that pile. But this will give us this will give us a float number. Pretend if we have a pile of 5, right? 5, and we eat at a rate of 2, it will take us 2, and then a 0.5. It will basically take us 2.5, but since of this constraint, we have to use up that whole hour on that pile. So we should actually take the ceiling. So 5 at a rate of 2 should output 3. So that's why we'll just capture a ceiling here. Format. So this is how many hours it's going to take given the rate. So we'll say hours taken equals self dot hours to eat given rate. And then we're going to be past the piles and we're going to give in the mid. So given the mid, right, we're going to see how many hours it takes. So if the hours taken, so pretend the amount of hours that were taken is less than or equal to h, or if the hours taken is, pretend the hours taken, it takes like 9 hours, right? Hour 9. Let me try to. Let's see. So okay, well let's think about our bounds here. We're binary searching for the rate, and this is where it gets tricky because we're given a rate here, but then we need to update the mid pointer based on the hours taken. And that's why it's a bit of a modified binary search in that way, where we're not just taking, like this part kind of trips me out a bit. So if the hours taken is greater, let's say the hours taken is actually greater than h. Let's say if it's greater than equal to h. If the hours taken is greater than equal to h, we're eating too slow. Or if it's greater than, we're eating too slow. So we need to move our left pointer up. So if the hours taken is greater than h, we need to take our left and we need to go mid plus 1. Because the hours taken to eat is greater than h, yeah. So we know our mid is too slow. So if we look anywhere to our left, those are even going to be slower, right? Else the hours taken is greater than or equal to, right? If it's greater than equal to, or sorry, if the hours taken is greater than, okay, this case is the hours taken is actually less than age. If the hours taken is less than age, we're moving too fast. So we need to move our right down. But if it's equal, then it's still fine, but we still want to move our right pointer down. So at the end, we just return the left here. And yeah, so that's how we solve that question right there. We're binary searching for a specific value, which is the rate at which we should eat bananas. It's a bit trippy. I just want to show the different variations of how we do that. So yeah, I showed how we can do a traditional binary search. I showed how we can binary search for a value. But like I mentioned, you'll never have to do binary search straight up. So in the next question, I'm going to show you one that you have to perform a modified binary search. I know people were asking me before, like, what is a modified binary search? And you'll get to know that in the next question. So this next question is a modified binary search. So we're tasked with finding the minimum in a rotated sorted array. So we start off with, we're given an array of length n, and it was in ascending order before, but now it got rotated. So for example, it started off as a regular array, but then it might have been rotated. So for example, given this array right here, it used to be like that. Pretend it was rotated 4 times. That means if it was rotated 4 times, rotated 4. That means we'll take 7. We'll take these 4 elements, 1, 2, 3, 4, and wrap them around because it got rotated 4, 5, 6, 7, and then just the regular. The other ones are still in order. 1, 2. So we get this. So you can see same as this. So yeah, that's what we mean by rotating it. It means just like sort of, if it was rotated once, then 7 would just wrap around here. That's once. If we rotate it twice, then we push all these elements 1 to the right. So 6 gets pushed off and rotated to the start. So it's kind of like, think about it like a circle. As we shift elements to the right, the other one wraps around. The other elements get put to the back. So this would be rotated twice. So we're pretty much tasked with returning the minimum element. So the minimum element, so the original, let's look at the first example. So we're looking for the minimum element. You can see that the original array was 1, 2, 3, 4, 5, and it was rotated 3 times. So the last 3 elements got put into the array here, to the back of the array. So we need to return the value of the smallest element, which is 1 here. And we need to do so in log of n time. And when I start seeing log n time, I automatically start thinking of a binary search. And since the input array is not actually sorted, it was actually rotated, we can't just use the traditional binary search. We have to modify the binary search. So how would I actually figure out how to do this? So the way I like to conceptualize this is, pretend we have a array that's sorted. That means the values sort of go up in this fashion right here. Pretend we have, for this example, we have 3, 4, 5, or the original array was simply 1, 2, 3, 4, 5, like this. So pretend that we actually rotated the array. What does it mean to rotate the array? That means it went from 1, 2, 3, 4, 5 to 3, 4, 5, 1, 2. 3, 4, 5, 1, 2. That means we kind of, so it went from this to something like this. Since we shifted it, what happened is, since we shifted by 3 elements, these elements, 1 and 2, sort of get pushed to the front here. This is how I could visualize it. And then 3, 4, 5, since it got shifted, it gets put to the front. Now the array sort of looks something like this. And we need to search inside the array to find the minimum element. The minimum element is this element right here. Right? So how are we going to do a binary search? Well, let's start with a left and right pointer. I like to visualize this question like this. And with binary search, we specify left and right pointers that show the bounds of our search space. And then we'll calculate some middle element. For this element, for this case, the middle element is, let me move this down here. The middle element would be 5. So what we're gonna do is we're gonna put a pointer right here. Right. The pointer is right on the middle at 5. And we're gonna compare 5 to the left boundary and the right boundary. What we're gonna do is we're gonna want to search on the side. So 5 is actually pointing at this point. It's actually like pointing right here. So what do we see here? We know that since we rotated the array, we know that one side is going to be sorted still. So this side is still sorted, and one side has a dip. One side was not sorted, is not sorted anymore. So there's a dip there. We want to find the side that has a dip in it, because the side that has a dip in it is the side because we essentially want to return the dip. So since we compare the left and the middle here and it's sorted, we know that the dip isn't here, and then we could sort of just search for the dip in the right side, right? So how do we know we'll know something is a dip is when we're looking at an element and then we look to its left and its left is actually larger than it. So that would be, so pretend, that's sort of how the solution would be there. Let's do a different example. Pretend we have like some sort of array here. And then we shifted this element. It used to be sorted, but now it turns here. Right. Say that we have our left and right, and then we point our middle. Our middle is here. Well, the middle and the right is completely sorted, but here the right is smaller than the left. So we know that the shift essentially, or the dip, is somewhere to the left, so we don't need to search the search space. Right. Pretend the middle, we calculate here. We calculate here. We see the left and right. We see the left and the middle is sorted, but then the middle and the right is not sorted. The left is actually larger than the right, so we could actually eliminate the search space right here because it's not sorted and the dip should be onto the right. So what we'll do is, again, like we'll move our left and right pointers here. And you could see how using that strategy, pretend we calculate a middle again here. We eliminate the side that's completely sorted. We see how we kind of zero in on where the dip is happening. That's how you solve this question. It's a bit tricky, but that's what a modified binary search is. There's a ton of questions like that. So what do we need to do? Like I mentioned, we need a left and right pointer. 0. And this is a modified. We're not just searching for values. We're kind of halving the search space every time still. So yeah, this is an interesting question. So while the left is less than, we know that there's an answer here. So what I do is, like, if I know the answer is going to be in the array, we know there's always an answer. We just say while left is less than, or we'll say while the left is equal to right. So what we're going to do is we're going to check. First, we're going to calculate our mid like in the last one. We go left plus right minus left divided by 2. Throw that all in brackets. So that captures our minimum. So that calculates our midpoint. Pretend we'll say like if the mid is greater than 0, what essentially is we're trying to find a dip, right? So we're trying to find any element that's less than the element right beside it, because that's when we know like where it was rotated. So we're seeing that's the dip there. So if the mid is greater than 0, because we don't want to look to the left at the bounds here, that we'll get index out of bounds. If the mid is greater than 0 and nums at mid is great, or nums at mid minus 1 is greater than nums at mid, that means, for example, mid was at this element. If the one behind me is greater than the current element, we know we're at the dip. We just return nums at mid. We just return this value. So that's when we exit this loop. Elif. So pretend we're at 5, right? This is the element. Or pretend pretend we're at 5. Or pretend we have let's rotate it once. Let's go 5, 1, 2, 3, 4. So pretend we're at the middle here. If the nums at the mid is less than the nums at the right, if it's completely sorted, right? If the nums at mid is less than the nums at the right, if it's completely sorted, we'll have a left and right pointer here. We're gonna want to move the right pointer equal to where our mid is at, because that could actually be part of the result. We don't know. We just know that this area is sorted, so we're good. But we still want to include 2 in the result, right? And then after, or we might not even care about that. We'll see. Maybe we can go mid minus 1. Let's see. Else left. Otherwise, let's just start with mid here, and we'll just move it down here. But now when we calculate, but pretend it wasn't sorted, then we move our left pointer. Else equals left equals mid plus 1. So that's the other case. So the other case is we're here. We have a left and right, and we have our mid. Pretend, like our nums mid is less than equal to right. No, it's not. Our nums mid is actually greater than it. So we know that we need to move our left pointer up and only search this area. So I would do mid plus 1. And I think from there, let's run that code. I think from there we just modify the binary search a bit. And what we do is while left is less than equal to right, minus 1 here. Wait, where am I? Nums mid is, if mid is greater than 0, we'll do less than right here, and then we'll just return nums at the left. The subtle changes here just to get it working. You see that beats 100% runtime and 80% memory, and you can see I had to finesse it a little bit in order to get it to work. You just learned little tricks there, but I think what we do is, I just want to show pretty much that how we're cutting the search space and how I work through that solution. So there might be a cleaner way to do this, but yeah, that was already 13 minutes on that question. That's a modified binary search. We're gonna get into one more question after this. So to finish off, let's go through the time and space complexity and some common pitfalls. So the time complexity, since we're cutting the search space in half every time, on every iteration, we're cutting it in half, and then on the next iteration, we're cutting that half and into another half. That leads to a log of n time complexity. For space complexity, most of the time we're just handling left and right pointers and adjusting them. So we most of the time it's only O of 1 space. If you did it recursively, it'd be log of n space. But yeah, just do it iteratively by having left and right pointers, and you can have a space complexity of O of 1, like I mentioned here. Pretty much the left and right, these are just variables. This is just a variable. Yeah, these are, you see how we're just pretty much just calculating variables. So we're not storing some data structure that's gonna take up too much space. And yeah, that's a time and space complexity log of n and space complexity O of 1. The common pitfalls I see is not understanding when to use binary search, not identifying binary search. So it only works on sorted data. So some people might not realize it's sorted and then perform some suboptimal linear search, or they might pretty much think it's sorted in some way or try to do binary search on non-sorted data. I see that, but that's more rare. Infinite loops, you can run into infinite loops a lot. Go ahead and try those 3 questions I showed and comment below if you get hit but with an infinite loop. It's pretty easy to get hit by infinite loop, especially if you're not adjusting the left and right pointers correctly. What else? You're not updating the bounds correctly. So you could see in the Coco eating bananas, I really had to think about how I was adjusting the bounds here. So yeah, try that question and try to really understand how you're gonna adjust the boundaries. But pretty much I see just people make mistakes on how they update the bounds. And then one that doesn't really happen in Python but will happen in other programming languages is overflowing on the mid calculation. So I pretty much show earlier in the video how to get away from overflowing in the mid calculation using a syntax like this: left plus right minus left divided by 2. But yeah, I think that's pretty much everything. See y'all in the next video.